Okay, ladies, so we are starting 10.1 today. Today's lesson will also be on your quiz, so make sure you are definitely paying attention to this. Tomorrow's lesson will not be on your quiz, but today's will be. Here are the answers from your calculator homework last night, the even answers. I'm not sure if the odd answers are in the back of your book or not, but here are the even answers to give you a good idea if you were doing it right. So check these. If you have any questions, like I said, you may go see Miss Wazalewski or Miss Brewer for help, or you can ask each other for help after class today. But the calculator will be on the quiz, so you do need to know how to use the calculator to figure out these answers. So I'll give you about a minute or two to check these answers real quick. Okay, so moving on to the notes, 10.1. Like we've talked about, a quadratic function has a degree of 2. We have standard form where the exponents are decreasing, and like we said, the shape is called a parabola. Um, in 10.2 and 10.3, we were talking about parabolas when there was a b value, but in 10.1, we're going to just look at when there's not a b value. So when there's not a b value, the axis of symmetry, if we recall, this is the formula, x equals negative b over 2a. Well, when there's no b value, it's negative 0 over whatever 2a may be, which will always be 0. So your axis of symmetry, when there is no b value, will always be at 0. Is always at x equals 0. So our parent quadratic function, the most basic one, remember the parent is the most basic one, is y equals x squared. A is 1, there's no b, and there's no c. And so we see what the parent function is at this picture below. The parent function has a vertex at 0, 0, always. What's also good to know is that there will always be points at the parent function at 1, 1 and negative 1, 1. Good for you to know. Makes it easier to graph when you're graphing the parent function if you can remember those 3 points. Okay, so and then like we said, the axis of symmetry is at x equals 0 when there's no b value. Make that bigger. So, like we've talked about, the graphs can get narrower, like we see in the red, or wider, like we see in the green. And the blue value is our parent function to compare. Remember when we talked about narrower, it's being pulled up faster. So we call that a vertical stretch. And we know we have a vertical stretch when our leading coefficient is bigger than 1. Remember, this does not mean that it's positive or negative. It just means that it's a number bigger than 1. And it's a vertical shrink, so this is when it's wider. Vertical stretch when it's narrow. a vertical shrink when a is a fraction that is less than 1. In this middle segment, we start worrying about the positive or negative. If it's positive, then we see that it's going to be opening up, like we've talked about. When it's negative, it'll open down, okay? But when we're comparing it to the parent function, we call it a reflection in the x-axis, like we see in both of these statements. So this red graph in the middle is a vertical stretch because it's narrow with a reflection in the x-axis because it's been flipped upside down. And we see that that happens when a is less than negative 1. We have a vertical shrink, so wider, with a reflection in the x-axis if a is between negative 1 and 0. So it's a fraction that's also negative. And then we call this last one. Here, in this picture at least, there's no shrink or stretch happening. But what we see here is that there's a c value. When we have a c value added on to the parent function, all that happens is the graph either moves up or down. It depends on what my c value is. If my c value is positive, then my graph will shift up, upward vertical translation. But I just call it a shift. If c is less than 0, if c is negative, then it's a shift downwards. So these are all comparisons to the parent function. You can have a vertical stretch or shrink. You can have a reflection in the x-axis, and you can have a vertical shift. Alright? Sometimes a graph will have all 3 of these. Sometimes a graph may only have 1. But know that all 3 of these can happen to one graph. Okay, so let's practice. We're going to first of all make a table of values for y equals 3x squared. Negative 2, negative 1, 0, 1, and 2 are always pretty good points to choose when we don't have a b or c value. Remember, when we have a b value, this is where my axis of symmetry is. So then negative 1 and 1 are just reflections. Okay, you'll see that in a second. So when y equals 3x squared, so if I plug in negative 2, I have 3 times a negative 2 squared, which is just 3 times 4, 12. When I plug in negative 1, I get 3 times 1, which is 3. When I plug in 0, get 3 times 0, which is just 0. When I plug in 1, I get 3 times 1, which is just 3. And when I plug in 2, I get 3 times 4 again, which is just 12. So like I said, negative 1 and 1 are just reflections, as we can see by the same y values. That's when our axis of symmetry is 0. So we go and we plot these points. Negative 2, 12 goes off my graph, so I'm not going to worry about it. Negative 1, 3. 1, 2, 3. 0, 0. 1, 3, and then 2, 12 also goes off my graph. So we graph those points, and that's what my graph looks like. The domain. Any parabola, remember, like I said, the domain is always all real numbers. But my range, let's look at this graph. If I look up pretty high, if I look up at the top, it's continuing to go up. There's no limits on how far up I can go. But as I look down, my graph only goes so far. It only goes to where y equals 0. So my range will be y greater than or equal to 0, because 0 is my lowest point, and it goes above 0, so greater than or equal to 0. Now let's look at a comparison. I can look to see if it was a stretch or shrink. I can look to see if it was a reflection, and I can look to see if it was shifted. As you should notice, it was stretched. It's narrower compared to my parent function, so we have a vertical stretch of 3. It was not reflected, nor was it shifted up or down. So that's my only comparison that I can make. You don't need to see the parent function to know what happened. You should be able to just look at this equation. Remember, a here is bigger than 1. So it's a vertical stretch. There's no c value to move it up or down, and it stays positive, so it hasn't been reflected. Okay, moving on. Alright, so we're going to compare this graph. Y equals negative 1/4 x squared. So I'm going to put this in my little process so I can work things out. So here we chose 4, 2, 0, 2, and 4. Because when I put in 1, I'll get a fraction, so I just avoided that process. So let's see, let's plug in. So when I plug in points, I get negative 4 squared. That's negative 1/4 times 16. That is negative 4. When I plug in negative 2, we get negative 1/4 times 2 squared, which is just 4. That's negative 1. When I plug in 0, I just get 0. When I plug in 2, I get negative 1/4 times 4 again, which is just negative 1. And when I plug in 4, get negative 1/4 times 16 again, which is negative 4. Okay, so now that I've made my table, let's go plot these points. Negative 4, negative 4, 1, 2, 3, 4, 1, 2, 3, 4, negative 2, negative 1, 0, 0, and then my reflected. So here's the graph that you get. like I said, any parabola, the domain is all real numbers. Now my range. If we look, there's no positive y values up here. My graph starts at 0 at y equals 0. That's also my max. So the rest of the graph is below 0. So my range is going to be y is less than or equal to 0. So there's my domain, there's my range. If I'm to compare it, what happened? Well, as I go back and look at my equation and look at my graph, the first thing I notice is that it's reflected over the x-axis. I think that's pretty obvious that it's been flipped. But if we look, my a value is less than 1, which means there is a vertical shrink. It's wider of 1/4. And that's my comparison to the parent function. Okay. So now we have y equals x squared plus 5. So we're going to compare it, we're going to graph it and then compare it. So again, I'm going to pick these points to use, -2, -1, 0, 1, and 2. Always good points to pick when we have no b value. Remember, when we have a b value, you find your x-axis, or your axis of symmetry first. But when we don't have a b value, we can just go make a table. So here I'm going to plug in -2 squared plus 5. Well, that's 9. -1 squared plus 5 is 6. 0 squared plus 5 is 5. 1 squared plus 5 is 6. And 2 squared plus 5 is 9. So we plot these points. There's my graph. Domain, still all real numbers. It still touch every x point in both directions. Now my range. If I look, it's facing up. So when it's facing up, it will always be y greater than or equal to. If it's facing down, it'll be y less than or equal to. Now I want to look to see where my max or my min is. Well, again, since it's facing up, it's a min, and it's here at 0, 5. So if I look, my range goes up from 5. So my range is y is greater than or equal to 5. When I compare it, there was no reflection, it's still facing up, and there was no stretch or shrink, and you can tell because my A value is 1, but there was a shift. There was a vertical shift up 5. It's important that you include the word vertical and that you tell me whether it went up or down. So a vertical shift up 5. So here, a combination of a couple things. Again, there's no B value, so I'm just going to jump right in to making a table. I'm going to pick the points here, so I don't have nasty fractions to deal with. I'm going to choose -2, -4, -2, 0, 2, and 4. When I plug in -1/2 times a -4 squared minus 4 gives me 1/2 times 16 minus 4. That's 8 minus 4, so 4. When I plug in -2, that's 1/2 times 4 minus 4. That gives me 2 minus 4, -2. 0. That will just be -4. When I plug in 2, remember there's no B value, so my axis of symmetry is at x equals 0. So -2 and 2 reflect, and 4 and -4 reflect. So this should get me -2. And if you plug it in and try it out, it does. 1/2 4 squared minus 4 should get me what -4 does. And when you plug it in, it does. So I'm going to plot these points, -4, 4. -2, -2. 0, -4. 2, -2, and 4, 4. there's my graph. Domain, again, all real numbers. Range, it's facing up, so it's y greater than or equal to. My lowest point is the -4, so y greater than or equal to -4. My comparison. Okay, so when you compare it to my parent function, the first thing that's obvious is that it was shifted down. So there was a vertical shift down of 4. And then the other thing that happened is that it got wider. Okay, so remember, wider means a vertical shrink of 1/2. And again, if you're having trouble seeing the vertical shrink, just look at your A value. My A value is 1/2, which means it's a vertical shrink. Alright, so looking at two equations, well, we're going to see what happens. So I start with this function, y equals x squared plus 6. How would that graph be affected if I changed it to y equals x squared plus 2? Well, I'm going from y equals x squared plus 6 to y equals x squared plus 2. What we notice, the only difference in these equations, and you can graph them if you want to, but it's going to take you way too much time. What we notice in these equations, the only thing that's different is this plus 6 and this plus 2. Well, how did I get from 6 to 2? Well, the only way I get from 6 to 2, you can treat it as an equation if you would like, is that I subtract 4. And this 6 and this 2 represent whether it was shifted up or down. So if I subtract 4 to get from my first equation to my second, then that means that the graph would shift 4 units down. Because my graph moved from y equals x squared plus 6 to y equals x squared plus 2. It was moved down. And our last problem. For my last problem, we have this solar energy. So a solar trough has a reflected parabolic surface used to collect solar energy. The rays are reflected from the surface toward a pipe that carries the water. The heated water produces steam that makes electricity. So the graph of the function, here's the function, models a cross-section where x and y are meters. All we're doing is using the graph to find the domain and range. Okay, well, here's our graph. It's this black line. So when I use that, my domain, again, is all real numbers, but let's talk about this. This is an actual trough. It's an actual half of a pipe. If I look at any pipe, does it continue on forever? No. But looking at my graph, here are the end points. Okay? So, when I look though where, for my x value, at least, where these endpoints are, I notice that this point is at 3, 4, 5. And this point is at 1, 2, 3, 4, 5, negative 5. So remember, domain is x. Well, the only x values are between negative 5 and 5. So my domain will also be between negative 5 and 5. My range, I'll draw in green. If we look at my range, remember my range are my y values. Well, my range starts here at 0, and it goes up to this point. Well, that point's not as easy to figure out. But those coordinates are 5 comma something and negative 5 comma something. So how would I figure out that y value? Well, all I have to do is just plug it in. Y equals 0.09 times 5 squared. 5 and negative 5 are going to give me the same answer, so you only need to do it once. You plug that into your calculator, and you get 2.25. So this height now is 2.25. So my range goes between the bottom of this trough at 0 to my highest point, 2.25. Again, it doesn't continue infinitely. It's an actual trough. That trough does not continue infinitely. So it's bounded. And that's the lesson for today. You may start your homework. Remember, this lesson is on your quiz that's on Thursday. So don't forget to study.